Hi, I'm Frank David from the biotech consulting firm Pharmagellan. This is episode number 3 of a 4-part series to help non-statisticians interpret time-to-event studies and Kaplan-Meier curves. In the prior 2 videos, I gave a general introduction to time-to-event studies and talked about how to interpret the hazard ratio and other numerical outputs. If you missed them, the links are in the description below. In the next few minutes, I'll cover the graphs themselves and what you can learn from them. Just to review, we're talking here about trials that track patients over time from when they get a drug until they have an event like death, hospitalization, or disease progression. The graphs look like up or down staircases, like the ones shown here. In this video, we'll look more closely at these graphs and see what we can learn from them beyond the summary statistics. Before we get started, 2 reminders. First, just like the other videos in this series, this one is aimed at biotech folks who aren't experts in statistics or trial design. If you're a biotech investor, banker, or med affairs or marketing pro, for example, you are in the bullseye of the intended audience. Second, if you find this video useful, stick around for the final installment on red flags in time-to-event studies. And also, check out our white paper and detailed book on analyzing biotech trials, both aimed at non-stats gurus. Links for all of these things are in the notes below. Okay, let's get started looking at the figures. As a reminder, even though the staircases go in different directions in these graphs, the underlying concepts are the same, and everything we'll talk about related to the figures holds true in both. As we discussed earlier, the x-axis is time, and the y-axis measures the percent of patients who either have had an event or remain event-free. If you need a refresher on the basic structure of these plots, please watch the first 2 videos in this series using the links in the description. In this episode, I'm going to go over some things you can learn by taking a close look at these figures. I'll cover 3 topics: censoring, curve divergence, and curve crossing. First, let's talk about the balance and distribution of censoring. I went over censoring and why it's important in the first video in this series, but right now let's focus on how censoring shows up graphically. Here's the Kaplan-Meier curve of overall survival from the Keynote-45 study of the PD-1 inhibitor Keytruda versus chemotherapy in urothelial carcinoma. The vertical hash marks on each line represent patients who were censored. You'll see these hash marks in almost all time-to-event studies that enroll up to a few hundred patients in each arm, although in much larger trials, they may not be shown. The censoring hash marks in this figure are mostly concentrated on the right-hand side of the graph. That's pretty typical because a lot of censoring is so-called administrative censoring, which happens when the trial ends. In Keynote-45, the minimum follow-up was about 10 months, so you'd expect relatively few patients to be censored before that time point. And that's what we see. Most of the hash marks are beyond that point, and they're probably patients who were recruited later during the trial. In contrast, some of the hash marks on the left-hand side of the figure can be due to other things, like dropouts due to side effects. If there are a lot of early censoring events, you probably want to take a minute and think about why that might be the case. Another thing to note in the Keynote-45 figure is that there's roughly the same amount of censoring in each arm. You don't need to get out a magnifying glass to count the hash marks. There will always be subtle differences in the number of censored events between the arms, especially at later time points. But, as I just said, almost all of these late censoring events are administrative ones that happen at the end of the trial and are just not very interesting. On the other hand, if there's a major imbalance, especially toward the left-hand side of the curve, you might worry about informative censoring. We'll talk more about that in the next video when we discuss red flags. Unfortunately, there are not strict rules for when you should be concerned about the censoring pattern in one of these graphs. The best thing you can do is study a lot of these curves so you can develop a sense for yourself of what distribution of censoring is typical versus not. The second thing to look at is when the curves diverge. In general, you expect to see the drug and control lines split from each other relatively early toward the left-hand side. As you move forward in time to the right-hand side of the graph, the gap between the lines should widen. That's what you see in this figure from a study of Vascepa's ability to prevent major cardiovascular events. But there are 2 more worrisome patterns that sometimes arise. A pretty obvious one is when the curves barely diverge at all, and the spread between them just never improves. Many people at medical meetings refer to this as the laser pointer test. If you can barely fit a laser pointer between the 2 curves, that's a bad sign. as we'll see in the video on red flags, that usually means the difference isn't very robust or doesn't matter clinically, regardless of what the stats say. The second common scenario is when the curves stay close together until near the end of the time period, and then the gap gets really big at the extreme right-hand side of the figure. Even though your eyes will probably get drawn to that big gap, you need to be careful not to put too much stock in that part of the figure, because those right-hand points are based on data from a much smaller number of patients, so you can't trust them as much. To understand why, let's think about how the uncertainty increases over time in one of these curves. You may have noticed that unlike many other biotech graphs, Kaplan-Meier and time-to-event figures almost never have any error bars. I'm not sure why that is, but it's generally true. But let's imagine what the error bars would look like if they were included. Toward the beginning of the study, you have the largest sample size you'll ever have, so all the data are from observed patients. But later on, the points on the lines are based on a mix of a smaller number of observations and a larger number of estimates of what would have happened to patients if they'd made it that long. So if the graph had error bars, you'd see their width increase as you move to the right to later time points. And in fact, that's what you see here in a rare example that does include 95% confidence intervals. This study compared active treatment with monitoring in patients with precancerous anal lesions, and as expected, the uncertainty gets steadily larger over time. The p-value was 0.03 in favor of treatment, but if you'd only seen the lines without the confidence intervals, you might have thought the difference was much more impressive because of the big gap on the right-hand side. One trick you can use to help you focus on what's important is to mentally ignore the parts of the curves where fewer than 20% of the patients remain at risk. Many time-to-event figures include a table that shows how many patients were event-free and uncensored in each arm at various time points. And when you see it, it is super helpful. For example, in Keynote 45, you can see that about 20% of the patients were still at risk around 12 or 14 months. So it would make sense to focus on the difference there, rather than all the way to the right at 20 months. It turns out not to matter much in this particular case, but in the next video on red flags, we'll see an example that's much more worrisome. Okay, so we've talked about censoring and curve divergence, so now let's discuss the third thing you should note in time-to-event figures, which is curve crossing. To do that, let's go back to the figure from Keynote 45. Before 4 months, the chemo group seems to be doing better than the Keytruda group. But then the curves cross, and after that point, Keytruda outperforms chemo. What's going on? It turns out that curve crossing is pretty common in immuno-oncology trials for reasons we'll discuss in the red flags episode of this series. But make no mistake about it, curve crossing is not normal, and you should always take note of it. The reason has to do with what statisticians call the proportional hazards assumption. In most time-to-event studies, the relative effect of the drug versus the control on the event rate is maintained over time. In other words, if you're twice as likely at 3 months to die on the control arm versus the drug arm, then that 2x ratio should be maintained at later time points too. But when the curves cross, like in Keynote 45, that means the ratio actually flipped. That's an extreme violation of the proportional hazards assumption, and it can really mess up the math when statisticians analyze these trials. Now, as I mentioned, this is a well-known phenomenon, especially in immuno-oncology, and it doesn't necessarily make the results of a time-to-event study invalid. But if you see the curves cross in an event study, it's almost always worth thinking about whether there's a plausible explanation and possibly getting input from a professional statistician to understand whether and how it might change your interpretation of the results. We'll come back to this in the next video on red flags. So just to review, we talked about 3 specific things to examine in a time-to-event graph or Kaplan-Meier curve. First was the distribution and timing of censoring. A massive imbalance between the arms and a lot of censoring at early time points are both causes for concern. Second was when the curves diverge. If there's barely any gap between the lines, or the gap is only visible at the latest time points, those are signs that the effect may not be particularly impressive or robust. And finally, we discussed curve crossing, which could indicate a violation of the proportional hazards assumption and make the stats less valid. So that's it for episode number 3 in this 4-part series on biotech time to event studies and Kaplan-Meier curves. Look below for the link to the final installment, where I'll go over the biggest red flags in these sorts of trials. And if you missed the first 2 episodes, you'll find links to them as well. Also, if biotech clinical trials are your jam, but you're not a stats expert, make sure to download our white paper on interpreting positive and negative study results, and also check out our soup to nuts handbook on how to analyze biotech trials. Links are in the description below and also at pharmagellan.com. Thanks for watching.